Okay, everyone, thank you for joining in. Tonight we are going to have a talk on microplastics in our lakes. And before we get started, I just want to let you know that we do have a couple webinars coming up. Next month, we'll be doing septic systems in our lakes. And then in April, we're going to do lake birds, beautiful and sometimes problematic. We'll talk a little bit about geese and what you can do to manage them. So tonight, Microplastics in Our Lakes, we are joined by Jill Emerson. She's from the Green Mountain Conservation Group, and she will introduce herself in just a moment. I'm going to go over a few housekeeping things first. Just so you know, our session is being recorded. We do ask that everyone stay muted and that you keep your cameras turned off during the webinar. That helps with bandwidth and any distracting background noise while we're presenting. We do have the option of using our chat box. So if during the presentation you have a question that comes up, please click that into our chat box at the end of the presentation. Kat and I will read those questions to Jill and hopefully get some answers for you. If we happen to know the answer during the presentation, we'll do our best to answer them, but we will most likely be leaving those to our experts tonight. Tomorrow, you're going to receive an evaluation form from us. Please share your feedback on the presentation. Let us know, if there's anything we should be doing that would improve these, or if there's anything that you think that we're doing good. We like to hear a good feedback too. And especially if you have ideas for future presentations, we're always looking for new ideas, things that our listeners want to hear about. Then you're also going to have an email come from us that's going to have all the links to the webinar. We get that posted online right away. So if you want to watch it again or share it with anyone, it will be available to you. Just a quick background about New Hampshire Lakes in case you're not familiar with us as an organization. We're the only publicly supported nonprofit working for all of New Hampshire's lakes, which there happens to be about 1,000 of them. You can support our efforts by becoming a supporter today right on our website at newhampshirelakes.org. Our mission is to keep lakes clean and healthy now and in the future. We work with partners and promote clean water policies and responsible use to inspire the public to take care of our lakes. And we do that many ways, but mostly through our 3 programs. Our advocacy program, which is in full swing right now. If you're interested in getting involved with some of our advocacy work, you can reach out to Michelle Davis. She is our advocacy program manager. We have our conservation program, and that's known for our lake host program, which is making sure invasive species are staying out of our lakes, and our newish Lake Smart program, and that's helping homeowners learn about things they can be doing on their own properties, whether they live on the lake or far from it, to keep our lakes clean. And that is a very cool program. So if you want to go to our website, you can start by taking a survey. Just it doesn't take very much time, and then you get immediate personalized feedback. So please check that out. And then also our outreach program brings you programs like this one tonight. And we are also hoping to have our in-person Lakes Congress again this year. Save the dates for that, June 2nd and 3rd. Your hosts this evening are me, Erin Mastine. I'm the Outreach Program Coordinator, and Kat is joining us tonight as well. She is our Conservation Program Assistant. We will be keeping an eye on the chat box, and we'll be bringing your questions to Jill at the end of the session. And without further ado, I will now turn it over to Jill. Thank you so much for joining us tonight. I am super excited to hear about your presentation. So I will stop sharing my screen and you are welcome to take over.
Great, thank you so much for having me. I love that I clearly gave you a super professional photo of me.
I love that photo.
Out on the river, doing some monitoring out there. All right, so let me see. I'm going to kind of ask the, I think, quintessential question everybody does. Can everybody see my screen?
Yes, looks good.
Okay, great. So hi, everyone. I'm Jill Emerson. I am the Water Quality Coordinator at Green Mountain Conservation Group. I'm very excited to be talking to you tonight about some of the work that our organization has been doing the last year, entailing microplastics. So support for this work comes from the New Hampshire State Conservation Commission, specifically the Moose Plate Grant Award. So before I really launch into the microplastics topic, I'd be remiss if I didn't say something about the Green Mountain Conservation Group. So we are a nonprofit that was founded in 1997, and we're a watershed organization that's pretty committed to conserving our shared natural resources, particularly clean water. Our area is located over the largest stratified drift aquifer in the state, so we take water protection very seriously. And we primarily work in 7 towns in our watershed. The work that we do is on 4 pillars, if you will. So we believe in the REAL principle, so research, which is the branch that I head up. We also do education, both adult and children programming. When the time comes for us to advocate for those natural resources, we do participate in advocacy. And finally, as many of you probably are aware, the best way to protect water is by protecting land. So not only do we do research, education, advocacy, we're also a land trust as well. Overall, we believe that if you have healthy waters, you have healthy communities. And in 2018, we opened up our brand new center, which you can see here with a big pile of snow on top of it from the most recent snowstorm. Normally in a non-pandemic time, we're open to the public. Right now we are, the facility is closed, but that being said, we're still doing outdoor programming, and we do have Zoom programming available on our website for anybody who is interested. So a little bit more about just where we are, because I've thrown around Ossipee watershed now a couple of times, and some of you might be going, where is that? Our center is located in Effingham, New Hampshire, which is and our building is pretty much as close as you can be to Maine without actually being in Maine. So I can go out my office door and spend 5 minutes walking down the road, and I am now in Maine. That's pretty much how close we are. The watershed that we do most of our work in is the Ossipee watershed, which is a sub-watershed of a larger Saco River basin. So the Saco River basin is pretty much split almost equally in half between New Hampshire and Maine. There's a tiny bit more in New Hampshire, and it encompasses about 1,700 square miles. So I'm not sure if everybody can see my pointer. Is your pointer? So over here is the Ossipee Lake. It's the big lake right in the middle here of this watershed map. It is either the 6th or the 7th largest lake in New Hampshire, and then off of it are a series of bays. And so this is primarily where the microplastics work I'm talking about will take place. Oops. Okay. Green Mountain is also a proud partner of the Lakes Region Conservation Corps, which means that we are an Americorps hub. Each year we have 2 full-term members who serve 10 months in our watershed, and 2 half-term members. And a lot of the work that you're going to see tonight was actually done by our Americorps during their term of service. So my right-hand person through most of this past year was my last year's Americorps member, Trent Milan. He's moved on to greener pastures now in Pennsylvania, but I had a tremendous amount of help from our education Americorps member, EB, and then our half-term member who hopped on in the summer, Spencer Wilson. And really this work couldn't have made the progress that it did without the 3 of them. We now have 2 new Americorps members, Caitlin and Bethany, who, if they're smart, they're on tonight because I am their supervisor. So they will be serving the next 10 months in the watershed, and they're starting to learn the ropes about how to do this research as well. So before I dive into our microplastics research, it's important to kind of know, how did we get ourselves into this situation where many of us are at least somewhat aware that there is a plastics issue globally. Plastics essentially just means anything that's pliable and easy to shape. So something that has a lot of versatility. In today's world, plastics tends to mean something that is manufactured, but 3,500 years ago, there were indigenous communities using natural plastics. So there's certain gum from trees that were utilized in tool making or for recreational material like balls and other things. And the plastics that we think about today really didn't start being developed until 1869. So in 1869, there was a New York firm that actually had a contest, $10,000 reward for anybody who could create a material that had a very similar texture and hardness that ivory did. At this point in the 1800s, humanity had done significant damage to the elephant population in harvesting of ivory. And so alternatives were trying to be developed for, okay, if we can't have ivory, what's something similar? So a man named John Hyatt actually developed the first synthetic polymer, which was a combination of cellulose and camphor. And he found that it had the durability and the same coloring as ivory. And this was really a tremendous discovery because up until this point in time, humanity had always had to harvest materials. You had to cut down trees, you had to mine ore from the ground and melt it down to make metals. But now we've actually created a polymer. 30 years later, Bakelite became the first synthetic plastic, meaning it was entirely made out of man-made molecules. None of it was natural. Bakelite was used heavily in the insulation of wires. So in the early 1900s, houses were starting to have electrical systems added to them, and Bakelite was a great insulator for that. Bakelite was versatile, it was easy to make, it was cheap. We could make it in large quantities and you could shape it into many different structures. From there, we had a series of wars, World War I and World War II. And if necessity is the mother of invention, I would argue that warfare is her father. Wars are great for developing new things, unfortunately. So we had metal rationings that were happening. So you couldn't purchase items that contained copper or aluminum. And so manufacturers were scrambling with how are we going to make products without using metals? And that's really where plastics took off. They were included in plane cockpits. They became part of soldiers' uniforms. They were used in synthetic tires, for nylon in ropes and in parachutes. And once the war ended, we never went back to that pre-war manufacturing style. And why would we? Plastic was cheap. It was quick to make. We didn't have to wait weeks or months to harvest materials. You could have it in days. And from there, production has increased to what we think of as plastic today. So as you can see in this chart, we basically went from having no plastic in 1917 to this modern day and age. We're now creating about 400+ million tons of plastic a year, which is just a tremendous amount of plastic, and it's really hard to wrap your head around. Here in the United States, we create more plastic waste than any other country, unfortunately. And the problem has gotten so pervasive that by 2050, there will be as much plastic per weight as there are fish in the ocean. So that's only 30 years from now that we're going to have this problem, which is, it's not that long. It's coming down the pike. So I'm not sure if you can see in here, there's actually a man in this bag monster. So his face is sort of up here and like, here's his shoe. This is Jed Barrier. He's a documentarian who did a series called Bag It. And what he's wearing here is what he refers to as his bag monster. So on average, a person uses 500 single-use plastic bags a year. And so this is his little creation that he's made to show what 500 single-use plastic bags looks like. And that's per person. And you use that bag for about 12 minutes and then you throw it away. Or if some of us may reuse it once or twice, but ultimately it gets about 12 minutes of use. So the problem with plastics is that they're incredibly hard to recycle if you can recycle them at all. So I know many of us have seen the triangles for recycling, and many of us probably when we were kids heard reduce, reuse, recycle. There's a reason that the last R on that is recycle. It's because that's the hardest thing to do. Plastics are identified from 1 through 7. So if you look at the bottom of any plastic item, you'll probably see one of those codes there. And that may make people feel like it's all able to be recycled because look, there's a recycling identification code. But in actuality, most of the plastic can't be recycled. In the town of Effingham, for example, we only recycle plastics 1, 2, and 5, and we're lucky that we have that plastic recycling at all. There's many towns that do not have plastic recycling anymore, or they may only take one type of plastic. In addition, we now have a new problem of in 2018 trying to stop taking our plastic items for recycling. So we're a little bit stuck now with the very little that we can recycle is really not being recycled anymore. We only recycle about 9% of the plastic that we try to recycle. So again, if you're making 400+ million tons of plastic and we're only recycling at best 9% of that, that other, millions of tons is going somewhere. And unfortunately, it's going directly into the environment. In many cases, places where there are landfills that plastic gets buried or burned tend to be in low-income communities or in communities of color. So they're also having an impact on the health and wealth and well-being of the people living in those communities. So this is a nice little graph from the WWF that shows the life cycle of some plastics. And what I want to stress is that since all of the components of plastic are not natural, those polymers, even as they break down, they're still existing in essentially an unnatural state in the environment. So, this is a little misleading saying the life cycle of plastics because there's still small bits of plastics that exist even when they're broken down. At a minimum, there's a recorded 260 species that have been impacted by plastic, but I would bet dollars to donuts that there's way more than that. These are just the ones that there's been studies behind. And the impacts can vary between reproductive issues, endocrine issues, inability, if you're a mollusk, to adhere to rocks, or just in many cases, animals will swallow bits of plastic and mistaking it for food, and then they're unable to intake any new nutrients. So because their bellies are so full of plastic that never leaves. In fact, 90% of birds, when they've been autopsied, have plastic in their guts. And 8 million tons of that plastic that we throw out or recycle is ending up in our oceans. So you can see from our little chart here, we're all guilty of at one point in our life using one or all of these things. And it's pretty tremendous to think that that plastic bag we used for 12 minutes is going to sit in our environment at a minimum of 20 years until it's broken down into smaller plastic pieces. So the other thing a lot of us are probably aware of is that now all of this plastic that's entering into our oceans is creating garbage patches. So every place where there is a gyre, there is a garbage patch, which typically is at a minimum one trash vortex. So basically the trash just moves around in a slow circle, depending on whether it's in the hot or cold current. The Great Pacific Garbage Patch is anywhere between 2 and 3 vortexes that are all working together. And one of the really dramatic things about people who have been out in the Great Pacific Garbage Patch is not only noticing the plastic that's floating along the top, is looking into the water and seeing a hazy, thick soup, if you will. So there's more plastic pollution there than what meets the eye. 60% of it is abandoned fishing equipment, unfortunately, but that means there's still 40% that is household garbage that has made its way into the ocean. And there is no place that you can go on planet Earth now and not find plastic, which is pretty tremendous if you think about it. So here are just a couple of different locations where plastic has been found. That might be surprising to some people. So the picture in the upper left here is of the Mariana Trench, so the deepest part of the ocean, and submarine footage has shown a plastic bag tumbling along the bottom, and you can see here bits of other plastic bags that have found their way to the deepest part of our ocean. Picture in the upper right is one of the base camps of Mount Everest. Mount Everest has a huge trash issue, to the point where Nepal in 2020 actually banned the use of some single-use plastic items. expeditions to Mount Everest are notorious for people bring up supplies and materials and then leave them there with no plans to ever retrieve them. In Antarctica recently, there was a survey done to see how much plastic was in the oceans around and within, or the waters within, excuse me, the waters within Antarctica. And they found 5 times more plastic than they had predicted. So it's infiltrating the bottom of the earth and at the top of the earth in the Arctic Circle. When scientists have done snow melt samples on in various places in the Arctic Circle that are hundreds of miles away from civilization, they have found microplastics or small bits of plastic in these snow samples as well. So there's really no place that you can go that there's not going to be plastic contamination. In many cases, plastic will take off in the atmosphere, and this is how it's traveling around the world, but also the water cycle will move those plastics around in a pretty efficient manner. So unfortunately, where you can't go anywhere in the world that doesn't have plastic, that also includes our bodies. So basically, if you do one of these 3 things, I do all of them. I eat, I drink, and I breathe. And if you're somebody who doesn't do one of these things, stay on at the end because I really want to talk to you. Unfortunately, you do have plastic in you. Sorry to gross everybody out. I'm sure you all just had dinner. So the type of plastic that you most likely have in you is known as microplastics. And I've thrown that term around a few times tonight. So let's define it. Term microplastics was originally coined in 2004 by a UK marine biologist who was noticing plastic in samples that he was collecting when he was out doing marine surveys. So for the purposes of tonight, we're going to just define all microplastics as anything being under 5 millimeters, which is about 1/5 of an inch. There are, with anything, subcategories. The smaller you get, you have different classifications, but tonight we're just going to treat anything that's less than 1/5 of an inch as a microplastic. There's essentially 2 kinds or 2 flavors of microplastic. You could be a primary microplastic, which you are purposefully produced to be small. A good example of that is microbeads, which are usually found in face washes, lotions, sunscreens, toothpastes. And in 2015, the Obama administration actually banned microbeads in products produced in the United States, which was a good first step. However, and there's always a but or a however, this doesn't include products that are made in other countries unless they too have a microbead ban. And that doesn't mean that your cosmetics and your lotions and your toothpaste don't have plastic in it. It just means they don't have microbeads. So there's other ways that there are plastic in those types of products. Microfibers are also arguably a primary microplastic. So the clothing that we wear, not all of it, but if you're wearing something that's polyester or nylon, you'll have plastic particles in there. Some of those microfibers are plastic based and they're all interwoven together, and you can actually see it shed off your clothing in your laundry. So a good example that I use when I'm teaching this to the kids is most people have a dryer and they've seen, their dryer punches out the wall of their house right to the outside, and all of the lint is just blowing directly into the environment. Well, if you have a lot of nylon and a lot of polyester clothing, you've now blown bits of plastic just right out into your backyard. The second type of microplastic is a secondary. So all that means pretty much is that it's broken down from a larger plastic item. And so those cases, we refer to those as microfragments. So microfragments don't really have a defined shape or size. Usually they look pretty scraggly, and they, often a variety of colors, but it's pretty much, it's an unknown piece of a larger object. So I hate polls when I do Zoom things because I'm terrible at them. And so rather than making everybody click in and try to do a poll, we're just going to do a quiet thought activity here. As I've told you, there is plastic in you if you eat, drink, or breathe. So how much plastic do you think you consume in a week? So I'm going to read you your options, and I want you to just in your head quietly think about which one I'm not sure hope is the right word, but which one you think is correct. So your choices are: you don't have any plastic in you. I wouldn't pick A. I'm already going to tell you that. B is you consume about the weight of a paperclip, so not the size, the weight. So think about how much a paperclip weighs when you hold it in your hand. So that's about 1 gram. Is it the weight of a penny? which is 2.5 grams? Is it the weight of a credit card, which is 5 grams? Or you can go with my personal favorite, which is E, which is I don't really want to know. Don't flip to the next slide and completely gross me out. Oh no, you're going to flip to the next slide, aren't you? So I'm going to give you like 2 seconds to think about which one you're going to pick. So congratulations to those of you who chose a credit card. A study from the University of Newcastle suggests that we ingest a credit card's worth of plastic a week. I like this image particularly because they're eating it with soy sauce, which is pretty much my go-to condiment. Depending on your lifestyle, you may consume more or less than 5 grams of microplastics a week. So if you adhere to a Mediterranean diet or you drink a lot of liquid that comes in bottles, you're probably exceeding that 5 grams of plastic. If you are more of a, I drink tap water and I do more farm to table-y types of things, you might have slightly less than 5 grams of plastic. But on average, it's about 5 grams a week. One of the at least interesting things to me, and might be slightly, scary may not be the word, but it's interesting that we don't really know what that's doing to us. So we're consuming this plastic and having no idea what the consequences are. There may be no consequences. It may be it goes right through our bodies, no harm, no foul, nothing to worry about. But as there's been a lot of studies on lower organisms that it is having an impact, if I was a betting woman, I would probably bet it is doing something, although we just don't know what. There have been some studies that show that compounds in plastics have altered the endocrine system, so altered hormones. There's actually been a really interesting paper that macrophages, which is part of our immune response, will eat plastics thinking it's an invasive in our bodies and then not quite know what to do with it once it's consumed it. In plastics, this is a broad sweeping generalization. There's about 144 different chemicals that can be used that are known to be toxic to human bodies. It's a potential that the plastic is a life raft for other organisms to come in on. It's really unknown at this point in time of what that plastic is doing to us. One of the things that I can tell you it's doing in lower organisms, though, is it's bioaccumulating in lower organisms. And what this essentially means is as lower organisms consume plastic, and then organisms higher up on the food chain consume those lower organisms, they're collecting all of that plastic. So here I've kind of created my own little pictorial diagram of that. So all the way on the left here, you can see this is a plankton. And the green illuminated thing in it is a piece of microfiber. So you can see that this plankton has now consumed microplastics. Fish will eat plankton in addition to consuming their own plastic, thinking that it's food. So if you think about all of the plankton that a fish will eat, in addition to eating its own plastic, it is inheriting, or is accumulating rather, all of that plastic from a lower organism that it has consumed. Then if we move up to a higher order organism like birds, which will consume a large number of fish per day or per week, in addition to consuming their own plastics that they mistake for food, it's now just inheriting the next level of plastic. So over time, this higher organisms will accumulate these plastics. And in some cases, it's really hard for them to get rid of. So what kind of led us down this path is we were originally doing cyanobacteria surveys, and every time we were pulling samples, we could see under the microscope all of this debris that was in some wild, unnatural colors. So bright pinks, bright purples, bright blues, things that I had a hard time trying to figure out what organism would possibly be like bright neon pink. And we figured we were looking at plastic debris in our Ossipee Lake system. So we started doing a little bit of poking around to see, could we find it in other things? So with a group of school kids, we actually took various commercial water. So think of a water bottle company. We probably ran it under a microscope at some point, and we were able to see a ton of debris. And we came up with a dye system where we could see the microplastics fluoresce, which I'm going to talk in more in depth in a little bit. But commercial water, our freshwater lakes, we were finding it. And the one that particularly grosses out the kids the most, it kind of ruined my childhood personally, was fresh snow. So there was a ton of debris in fresh snow, and this really made us want to explore what could we find in our lakes, because we're clearly seeing this everywhere, and how much plastic is in our freshwater lakes in New Hampshire. As we started doing a literature review, what we were finding is that there is really a knowledge gap for freshwater systems. So this is not an exhaustive by any means compilation of other microplastic surveys that have happened. And if you look at this chart, everything that's in green is a marine system and everything in blue is a freshwater system. And it's easy to see that there's way more information on marine systems than there are on freshwater systems. Fortunately, that is starting to change and there is more information available on freshwater systems, but there's still tons of knowledge gaps in our freshwater systems. So when we were trying to figure out our protocols, we had to keep in mind that what we were taking from marine data collections may not be 100% translatable to freshwater samples. So we decided that we were going to do sort of a four-pronged targeted approach at looking at microplastics in our lake. So this is, again, the Lake Ossipee system. So here's what we refer to as the big lake. And then off of it is a series of bays, and including up here. So we decided we were going to look at water in two different ways. We were going to take a water collection from the deep spot. We do lake monitoring anyway at the deep spot, so let's collect some microplastic samples. We also decided that we were going to do a manta trawl in the channels in between the bays, and I'm going to explain what that means in a little bit, but basically we were going to take some surface water samples. We also decided to look at sediment or sand samples from 3 different locations to see over time how much plastic had washed up on our beaches. And finally, we wanted to see, was the plastic entering into the food web? So we decided to take plankton samples as well. So a little more in depth of that protocol, water collection was done May through September as we were doing our lake monitoring. And we identified the deep spot by both GPS and the depth finder. So you can see up here, one of our Americorps members has a depth finder and another one's working with our GPS. We decided that we were going to sample at about 8 meters or so down. We tried to take our deep water sample to the thermocline, which is essentially lakes divide into 3 layers in the summer. And this middle section here is considered the thermocline. So it was roughly about 8 meters or a little more than 24 feet down that we were taking a water column sample. And in addition, we took the manta trawl samples in between the bays. And here are some closer up pictures of, I keep saying manta trawl and what is that? It might be helpful to think of it as a giant windsock, but for the water. So we had this giant 8 to 10 foot net that we threw out behind the back of the boat, and we trolled at about 2 knots speed or so, and made sure that our manta was behind the wake of the boat, and we collected in a very slow moving way water and filtered it out in real time. So I don't know if you can see, here's the little basket that the sample gets collected into. And we used a very small pore size net. So we were really trying to capture as much plastic as we could, but we also have to have a pore that's big enough for the water to filter through. This net is incredibly heavy, which was something we hadn't planned on, at least I hadn't planned on. So pulling it up for the first time, I thought I was going to go into the drink for a minute, but I was much better prepared the second time I had to pull it up onto the boat. So for our sediment collection, we chose 3 locations around the Ossipee Lake, and we created a 5 meter, or excuse me, a half meter by a half meter grid. So about 1.5 feet by 1.5 feet square. And we did this at the rack line. So the rack line is that section of the beach where debris washes up on shore. So you can go out to almost any beach and find the rack line just from looking for the leaf litter, the pine needles, the pine cones, the tree branches. So here you can see Caitlin is working at one of our locations. We removed as much leaf litter or pine cones that we could without disturbing our sample, because we didn't really want to have the leaves and other debris in our sediment sample. We also put the sediment through a large pore sifter just to collect rocks and other debris, because again, we didn't really want that in our samples. We took all of the sand back to our headquarters, we dried it, and then we mixed that sediment with a high molar salt solution. So the goal there is to create a high density solution so that your sediment would sink. And because that salt water is so dense, it would float the plastic to the top, and then you could pull off the top of the sample, leaving your sediment behind. And then finally, our plankton collection we did at the deep spot. So here you can see Trent and I with our plankton net. We usually did one to two pulls, excuse me, at each spot. The goal there was just to try to collect as much plankton as we possibly could. When we got back to the office, we filtered and pooled all of the plankton from all the bays together. We dried them in an oven overnight, and then we ground them up to try to break open the plankton as much as we possibly could. Once we had our, essentially our plankton powder, we then added a base to it to try to digest all of the organic debris that was in there. So now our poor plankton that's been dried and ground up, it's now being digested with a base. And after 24 hours of that, we neutralized it so we didn't burn our hands. So then we just had a water and a salt solution, and we treated it as a water sample from there. We didn't do any sort of plankton counts because this was our pilot year, and a lot of this was just like, hey, let's see if it works. But a casual observation showed that a lot of our plankton were either water fleas or rotifers, which are a pretty common plankton to New Hampshire. So once we had everything sort of into this aqueous solution, we then treated all of our samples with this dye called NyloRed. And I know that I've said NyloRed a few times here. This is the dye that gives the plastic that fluorescent glow that you saw in the pictures previously. So originally this dye was used to stain lipids, but it's kind of been co-opted now into a lot of microplastics research. And there's a tremendous body of knowledge on NyloRed out there for people to explore if they want to do some additional reading. I've never found quite a great example as to why NyloRed works. It's most likely working through hydrophobic interactions. So water is pretty polar, plastic in many cases is not, and like wants to play with like. So the dye will adhere to the non-polar things essentially. Once we've treated with our dye, we let our samples sit usually overnight to let them dry. And then we do an excitation via blue light. So I actually have this like wicked bright blue light that Americorps members quickly learn not to look directly into. And it's literally one that crime scene investigators use because that's where I bought it from, which was a very interesting order for our bookkeeper. I fight crime on the weekends. So we shine this bright blue light on our sample, and then we snap a photo through an orange lens. So this is any orange lens that you could find at your local photography place. So what we did just to see if it would even work, because reading things from other labs is great, but when you actually get the materials in your hands, it's nice to know those that actually work. We did a little controlled experiment here. So we took some filtered water and put it onto our gridded filter paper and then treated it with NyloRed and did the excitation. And we didn't really see much of interest in this. If you are looking at this, you can see that there's little pinpricks of light in there. And upon closer evaluation, we realized we were having some non-specific binding happening directly to our filter with the dye for some reason that wasn't super consistent. However, when we added in the plastic samples, which is all of this bright yellow, almost white looking material in this sample, we could see that our dye and our system was picking up those microplastic samples. I had one of my poor Americorps members literally cheese grate the side of I think, laundry detergent bottle to create small pieces of plastic that we could see with the naked eye, but then also could see illuminate, because we just wanted to make sure what we were looking at was plastic. So the system works. Throughout this entire journey, one of the hardest parts of all of this was trying to figure out how on earth to do any of this without introducing more areas of plastic contamination. So if you think about If you've ever done lake monitoring, or if you've ever even been in a science lab at all, a lot of the materials are plastic based. We use plastic bottles and plastic hoses and plastic collection containers and plastic pipettes, and it's everywhere. So we had to come up with workarounds for many of the steps. So collection containers became mason jars, which had their own series of problems, because if you drop a mason jar on a boat, it breaks. We swapped out plastics for glass and ceramic and metal alternatives in every place that we could. And we ended up having to take calculated risks when a good alternative didn't present itself. And that's something that we're going to keep working on for the very few places where there was plastic where we couldn't come up with an alternative of, is there an alternative out there? Then we just didn't find it. So it really added an element that, at least in my scientific career, I never had to worry about, because it never mattered if something had plastic contamination in it. But when you're doing a plastic survey, it absolutely matters. So here's our initial findings with some more bright colored pictures for everybody to look at. So the initial way that we had hoped to do this, that we had to quickly abandon, is we were hoping we could take a full plate image, which this is one sample and the entire Petri plate that we're looking at. When we did it this way, we were finding we were missing out on a tremendous amount of the smaller plastics. So in this picture, you can see that there's 4 really bright colored sections amid all of this orange. And those are 4 very large pieces of microplastic. But when we started looking at it through a microscope, we were finding more plastic than what our total Petri image found. So here in the middle, you can see what on average we found in a 100 ml sample. So 100 mils is somewhere around about half a cup or so of water. So it's not a lot of water. I think it's 3.5 ounces or 4 ounces. It's somewhere in that range. So we're talking about a really small amount of water. And this is what we were finding in our deep water samples. So we were finding anywhere between 30 and 65 pieces of microplastic just in that 3.5 ounce sample. In our manta trawl, we were on average finding about 80 pieces in the same, which was also water filtered as it was trolling along the bay. We didn't get as many manta samples as we had hoped for, because with the pandemic, unfortunately, we have shipping issues. So we had ordered this manta trawl in May and it didn't show up until August. So it kind of cut into our sampling season. So I like to think that if we had had more opportunities to launch this, which we will this summer, because now we have it, that number is probably going to increase. You can see in chart form that we definitely had one bay that had consistently more plastic than the others, which was our Danforth Bay. It's sort of located in the upper region of that Ossipee Lake system. But down below, you can see here are some of our images that we've collected of the plastic in the water. So here you can see some on the left, some micro beads, and this one's a nice bead with a fiber here, nice little illuminated fiber. Here, there's a couple of different fibers. There's some in bright yellow, and then there's actually a red one here. The difference in color most likely is a different plastic material. There's been some studies that have shown that the RGB content, so the red, green, blue value that you get can tell you what type of plastic it is. We've not, at Green Mountain, we've not gotten there yet, but that's something that I'm hopeful that we can do, is then evaluate what types of, not only is it a bead, a fiber, a fragment, but what is the actual plastic material. And then finally, here were a couple of different cool pieces of microfragments that we found. So we were finding, unsurprisingly, plastic in our aquatic system. For plankton, in total, we had 3 plankton pulls. Unfortunately, one of the lessons we learned, again, with the mason jars is when you drop them, they break. So we did lose one of our plankton samples to breakage, unfortunately. But in the 3 plankton pulls that we were able to do over the summer, we found 57 microplastic pieces in total, with 19 being the average found per sampling event. And off to the right here, you could see a series of different photographs that we've taken of microplastics we found in our little plankton buoys. There are areas of improvements that I'm hoping we can make next year, because again, last year was the first year we tried any of this. So we're hoping that we can gather more plankton and come up with a couple of steps in between that should help improve our visual our ability to see the microplastics. The plankton tended to have a lot of debris left over in it, which we think was interfering with our ability to see a lot of the plastic. So that's one of the ways that we're going to try to clean that up this summer. And we're also interested in the future of now looking at the mollusk population. So mollusks are the filtration systems of lakes. So they probably have intake, they probably do intake microplastics, and it would be really interesting to see how many microplastics we find in the mollusk population. So maybe New Hampshire Lakes will have me back next year to talk about that. Finally, the sediment part of this is what we're currently working on now in the office. This is one of my new Americorps members, Bethany here, working hard on a sand sample, getting it ready for drying. We've had some preliminary work done in this, but nothing that I feel confident on reporting on tonight. One of the big battles that we seem to be fighting is the salt is creating almost like salt flats in our sample, and it's making it really hard to see the filter itself once it's dried. And we're also playing around with, instead of using sodium chloride as our salt, of using sodium iodide, which creates a denser solution. But as one of the sort of background plagues of this entire project has been supply chain issues. So every time we order something, it's taking weeks or months to come in. So this project for the sediment has kind of gone in fits and spurts, but it seems like we're just now getting all of the materials we need to move forward on this. So stay tuned on that, but we're getting a good protocol down. So I feel confident in the next couple of weeks we'll have this nailed down pretty good. For those of you who are interested in potentially using a NyloRed type system in your lakes, there are pros and cons to it. It's pretty cheap to run microplastic samples this way. So a lot of the studies that I read that were not utilizing NyloRed as their identification systems tended to use instrumentation that costs $100,000, which is great if you work at a university, but not great if you're a small nonprofit. So they're pretty cheap to run. This protocol was pretty easy to use. It's pretty forgiving in a lot of different ways. You can process a sample, and then if you need to leave for 4 days, you can come back to it and you can still do the fluorescence without any detriment to the sample. This has been a tremendous education tool for us, for adults and kids. Everybody likes to look at glowing plastic samples, but it starts to get them to think about all the ways that plastic has infiltrated the environment. And usually, particularly with the school children, it's not something that they've really had a lot of exposure to. So we have just really found the NyloRed to be a very impactful tool for the local kids. And in many cases, it's sometimes their first use of a microscope. So not only are they learning a little bit about water, learning about chemistry and about fluorescence, they're also learning microscopy, which is pretty cool. And finally, there is a reasonable amount of information out there of scientific journal publications that show NyloRed is a valid tool for microplastic study. The one takeaway, every paper and everybody that we talk to about doing this said is that you're going to have to come up with the protocol that works for your lake system. There are a few cons that I'd be, again, remiss not to mention. It seems that it only binds to nonpolar plastic, and some plastic is polar. So some of it does have charge. So we're probably missing some of those plastics. And in our hands, we have seen that it does bind to organic. So we do use other cues like the phenotypes, or what the shape, or what does it look like under white light, to help us identify or at least feel a little more confident if we're looking at plastic. And there also does tend to be a difference in fluorescence. So the plastic is pretty much hits you in the face with its vibrancy, whereas the organics, you do see a little bit of a signal, but it tends to not be as nearly as dramatic as plastic does. So it's a system I would highly recommend if other lakes want to take a look at their microplastic situation. I would highly recommend this NyloRed system. And again, we've taken this show on the road, if you will, and we've gone to local camps. We went to summer school. Spencer Wilson, one of our half-term members, was really instrumental in creating educational content around this microplastic stuff. Here are Trent Eby and I in the middle, being our own little plastic polymer to show kids how polymers are formed. And if you are an educator, or you're another nonprofit who's on tonight looking for educational programming, we have a Less Plastic guide on our website that follows next generation science standards. That's free and open for the public to use. And if you read it and you've got questions on the experiments, you can feel free to give us a holler on it, because we're happy to help. We're really excited that we've developed this education around this. And that education is targeted from kindergarten through seniors in high school. So pretty much all ages will find something in this guide. So this fall, we had the different schools pilot microplastics collection. So they were collecting their own samples, and then I was staining it for them and sending them back photos so that they could see in their own environments what they were able to collect. So here you can see some of the kids out in the river using plankton nets. So they had to follow a protocol. They got to use plankton nets that they've never used before. Again, microscopy that they've never done. And this is really where we got to see the power of this research when we brought it into the school system. So it was really successful, and we're going to implement it into more of our programming in the next year. So if I have depressed you greatly, I'm truly sorry. There are things one can do. There's different legislation out there that comes and goes in fits and spurts that I would encourage everybody to support. Maine has done a good job in the recent years of having producer responsibility acts. I would encourage you first to refuse plastic before you reduce, reuse, recycle, because if it's not there, then you don't have to worry about the other 3 R's. And finally, you can participate in different science, community science programs. Nat Geo's got one, a debris tracker, and you can also do plastic audits to see if there's a certain company maybe that has more plastic litter. If you do a road cleanup of who's one of the bigger plastic producers, that you could letter write to and ask them to change their behaviors. I'd like to thank the New Hampshire State Conservation Commission, the Moose Plate Grant, for allowing me to do this. So if you thought this was cool tonight and you're also in need of a new license plate, think about sponsoring the New Hampshire SCC. We really couldn't have bought the equipment and got this off the ground without their help. And so just a tremendous thanks to them. And we tried as much as we could to bring around our little sign that I unfortunately forgot quite a few times to bring with us, but honestly, we can't thank them enough for their support on this. We also had tremendous amount of help in partners and research collaborators and people who helped us in education. And so here's a huge list of them. And generally speaking, it's various libraries and various schools in our area, but we also had help from Dora Foundation, the Americorps program, and Jeb Barrier Baggett came and did a talk with us last year, and it was really cool. Finally, thank you specifically to the people who helped me actually out in the field, or in the water in this case, collect plastics. So here's a photo of them at various points throughout the summer helping out. And Linda Habiff was our boat driver, and I couldn't thank her enough. Of every time we needed to go out, she was willing to let us borrow her boat and allow us to throw random junk off the back end of it and learn how to troll it. And so she was incredibly graceful and so kind, and I can't thank her enough. But thank you to all of these people. And finally, if you want to know more about this program or other things, here's all of our contact information, and off to the right here are some of the photos of the other things that we have participated in the last couple of years. And with that, I'll take any questions, and thank you again to New Hampshire Lakes for having me tonight.
Thank you, Jill. That was fascinating and, like you said, slightly depressing. So this is a topic that I'm super interested in. So I want to thank you, because there's a lot of information out there about plastics in our oceans, but nothing close to home like this certainly is. Let's see what we might have for questions here.
We had one question.
Oh, go ahead, Kat. Thank you.
We had a question. This is from Cynthia Walter. If microplastic is deposited with each snowfall, would you expect microplastic abundance in the lake to peak just after snowmelt?
Oh, that's a good question. I think in terms of peaking, I would honestly expect it right as snow melt is occurring. That would probably be the time we would see the most plastic. We did not sample in April. We did sample in May. But I would say that that's probably a pretty solid guess. Now you've got me thinking of, like, how can I do that and test it? And But yeah, I would say that's probably a good guess.
Let's see, what else do we have? We do have a couple people posting about other places you can find some information about plastics. So just in case anybody doesn't know, we do make a copy of our chat box and provide that on our website. So anything that people are putting in here that are great places to find additional information, those are available to you after the Zoom meeting is over. So I will just go ahead and keep scrolling and take a look for any additional questions we might have. Bonnie Christie's asking, do you think we would see the same sort of results in our rivers?
Yes, to an extent. As rivers flush, it might be slightly harder to capture. What we do with our river samples right now that we piloted with the kids is to put a plankton net in and let it sit for an hour. And then collect the plastic. And I'm trying to remember off the top of my head what those values were and if they were similar to what we found in the lake. And I think they were, after an hour of filtering through the plankton net, I think they were relatively similar. But I would expect in any sort of aqueous environment that you're going to find microplastics in areas that are, if your river is in a more urban developed region, I would imagine you would find more than something that is more in a rural, undeveloped location. So I think it also depends on where your river is located. So in our area, many of our streams are not in, we don't have a tremendous amount of urban development. We do have some. But one of the things that I am hopeful to do in the future is to set up nets at various river locations and collect some microplastics data for that too. It was just, we started this project in May and a lot of the prelim steps was just getting it to work. And now that we have a functional system, we're really hopeful that we can expand in other ways, including looking at snow melt. So yeah, to answer your question, I think if your river's in a populated place, we would find more microplastics.
Yep. Let's see what else. This is a question maybe you have an answer to. Do you know about the New Hampshire legislature's bill to study extended producer responsibility?
I do not. Legislation unfortunately tends to happen in fits and spurts, and it seems like getting anything to pass that is whether it's limiting single-use plastics or trying to have manufacturers being more responsible for their plastic manufacturing, it seems like it's always an uphill battle to get any of those to pass. So I'm not sure what the current legislation is. So I'm not sure if there's a specific question about that legislation or just more wondering if I am aware of it. Not sure I answered that satisfactorily.
Not something we would necessarily expect you to know the answer to, so don't worry about it. Here's one that you could possibly answer. What things do you do to prevent microplastics coming out of your laundry from drying or from washing?
So the best things to do, honestly, is to just wash clothes less. If you have to wash items, spot washing tends to help eliminate some of the plastic shedding. There is some hypotheses out there that buying things that have been thrifted, pretty much your first or second wash is really the things that are going to shed the most plastic off of an article of clothing. So if you tend to do more thrift shopping, it's probably whatever plastic impact that shirt's going to have, it's already had to some degree. You can buy filters for your washing machine that will collect the microplastics, but then all you're doing in that case is you're moving it into the trash. So you're keeping it, you're taking it out of one system, but you're putting it into another. So it's kind of a lateral move in that case. Honestly, buying items that are not synthetically made is probably your best bet of, or best course of action of buying things that are 100% cotton and 100% wool. And when you can't, thrifting what you can. Fast fashion in its own right is a huge detriment to the environment for many instances, but one of them is just the tremendous amount of waste that they cause. So if you can thrift something, I would recommend thrifting. It's also better for your wallet too.
Okay, well, we have lots of thank yous for the presentation in our chat. So I do want to say thank you as well. And we have some recommendations, like you said, a filter that you could put in the wash. Let's see, here's an interesting one from Cynthia. Has anyone compared micro versus larger plastic in lakes that are ringed by cottages versus forest? In other words, is there evidence that the microplastic comes from breakdown of local plastic?
I'm not aware of anybody who has done that specifically. There's been, there was a really neat study that was done on atmospheric deposition of microplastics, which is, I think one can draw parallels from to this question. They set up collection units in actually various national parks throughout the Midwest and the West. And every time there was a storm that blew in from urban populated area, there tended to be larger pieces and more microplastic than when winds were from more rural locations. And so I think you can probably extrapolate that experiment into what would happen in the scenario that Cynthia posed. But I'm not sure if anybody's actually done that comparison with larger versus smaller plastics in lakes that have cottages versus forest. You're always going to find plastic in anywhere that you look due to atmospheric deposition. I think what that atmospheric deposition experiment that I just described did show is that urban areas are always going to have more plastic. So I think the more houses that you have, the more plastic is going to be into that system. So my guess is if you had a very populated lake, you're probably going to find way more plastic than if you had this, you know, secluded pond that doesn't really have much development around it.
Yeah, that makes sense. Well, we've hit 8 o'clock, so I'm going to conclude our presentation for this evening. Jill, thanks again so much for bringing this to us and for all the work that the Green Mountain Conservation Group is doing. You guys recently launched a new Salt Responsibly campaign that is great that we've been sharing on our social media. So thank you for that as well. And just a reminder, this will be up tomorrow for anyone that wants to share with friends. And we hope you all have a great evening. And thank you again, Jill, for joining us tonight.
Thanks for having me. Have a good night, everyone.
Bye.